for example, one of the things that I've worked on a lot while I was getting my degrees was imaging problems. So you can imagine, for example, let's say, something, well, let's say, something, there's some sort of like natural disaster, like a giant flood or a mudslide or something like that, which we have the capability to kind of view the details of the event happening in real time. Let's say we're taking a video of it, or we have some satellite recordings or something like that is going on. What we should be able to do in the future with a quantum computer is process those images in real time with highly, with very little data loss, and perhaps, have better outcomes, better predictions as to like where resources need to be immediately allocated in order to help people and our infrastructure with those sorts of events. So that's kind of like the big picture, like in the future, this is where we would want to be with this quantum technology. But again, right now we're in this scale where we're in this space where maybe we are not quite ready for that yet. But what my company does, Quantum Computing Inc., what my company does is we try to build quantum solutions. So we try and take the limited capabilities that we have right now, but use those limited capabilities in such a way that we can start moving towards solving big problems like that. And doing that by providing the tools companies need to focus on where we're going to find this quantum advantage. And that can mean different things. It can mean like solving really large optimization problems. It means things like providing a link to different quantum computing providers like Rigetti, and the D-Wave machine. So I just wanted to provide a little bit of background and a little bit of details on where we hope this quantum world is going to head at QCI. But today we're going to talk about quantum machine learning, which is going to be a big part of getting the most we can out of these current quantum machines. So I wanted to, oops, I'm on the wrong screen. There we go. So I wanted to talk about what quantum machine learning really means in a sense. And in the literature, quantum machine learning refers to any combination of quantum or classical data and classical machine learning or machine learning on a specific quantum machine. So any of these big picture ideas has been described as quantum machine learning. At QCI, we really focus on thinking about classical data that companies have right now, and how we can apply some sort of quantum process to that classical data. So in my line of work, I typically start here with classical data, and I move along these kind of arrows, mapping things into either quantum data, mapping things using some classical machine learning. And I eventually want to get down to a place where I'm actually using a quantum machine to do some processes that tell me information about this classical data again. So I'm typically kind of looking to get back, starting here, move along the arrows to get to this corner here. So that's kind of the context that we're going to be talking about today. And I wanted to start with just an example that we solve in classical machine learning. So machine learning that we're used to right now, the type of machine learning models that we have on our cell phones, that Google uses, things like that. So for a simple example, let's talk about image classification. So for example, this is a large field in machine learning. This technology is used in all sorts of things from, like I said, your cell phones to self-driving cars. But here at the basic level, what we want to do is take a set of images and say something about those images. For example, like if we have a large collection of images of, everybody's pets on the call right now, we may want to say, okay, well, which of these images has a cat in it? So that's an example of an image classification where our data are images of pets. Maybe the model that we choose to use, the machine learning model that we choose to use, is a neural network. And our prediction will be whether or not that image has a cat or doesn't have a cat. So for these examples, I'm going to focus on a data science-based approach where we look at these specific 4 things that I have listed on the screen. We'll ask ourselves, what sort of data are we operating on? What sort of model are we using? What type of prediction do I want out of this model? And then how am I going to know that I have a good prediction? How am I going to train my model to give me what I want out of this data? So let's look at this in a classical sense. So we have classical data, those are images, and we'll use a classical machine learning model, a standard neural network. So we're just kind of focusing on this pipeline right here. So no quantum yet. And we'll get to quantum in a second. So first off, how does this work kind of in the classical machine learning sense? Well, here is the structure. This trained model is in the form of a neural network. Our data is here. We have a picture of a cat here. And then our prediction is at the end where it says, yes, this is an actual cat. Now, briefly, I want to talk about how data flows through this neural network model. Here in this layer, this input layer, we take all of the individual pixels, so all of the little pieces of information that are contained in the image, and we feed it through each of these nodes. So each of these nodes gets a piece of information. Whoops, went too far. Each of these nodes get a piece of information from this image, and then it's fed through, why is it doing this? Sorry about that. Okay, it's fed through this, I can't control my slides. Okay, hopefully it won't do that again. We get fed through each of these, this graph sort of structure where each of the input pieces of information gets sent to each of these hidden layer nodes and is combined in a different way so that the network itself will pick up characteristics of this image that will help the network identify whether or not this is a cat. So some of the things that it looks for in these images, in the image itself, or some of the things that these nodes filter out will be like structural items in the image itself. And of course, this depends on how your neural network is structured. But for example, let's say we take all this information and we look at the path that goes through this node and then goes through this node. And what we may see is that if we look at the data flowing through that path, we may see that like, okay, that's going to pick up a paw. So it's going to look and find, you know, where is there a paw in this image? That's the type of question that that path will ask. And if it finds a paw, then maybe it says, okay, this is very much a characteristic of a cat picture. There is a paw there. So that's how kind of the neural network structure works. But it doesn't do that automatically. Each of these nodes has to be told kind of whether or not it's doing a good job picking up on those characteristics. So to do that, now I want to move the slides. Now we see we have to implement a training procedure. So in order to implement a training procedure, what we do is we first present data to this model architecture, so this neural network structure. We calculate some prediction, and maybe it's not a very good prediction at first. That's okay, because what we'll do is we'll assess how wrong the prediction is. So we'll calculate this error. And then what we do is we feed the error backwards through the network. We kind of adjust things in the network very slightly. And then we feed the data again. We get a new prediction, and hopefully it's a better prediction. Hopefully it's more up here. We assess that error and we do the same thing again. And we do this through our entire data set. that's why when you hear about machine learning models, they need lots and lots of data. It's because of this training process. We have to feed everything through the network. We have to look at our prediction in the end, and then we kind of adjust it slowly, and then we repeat the process again. So we want to see all different sorts of pictures of cats and not cats in order to get a good model that's going to tell us when we present a new picture, this has a cat in it or this doesn't have a cat in it. So now, how does this involve quantum, or how can we fit a quantum computer into this process? So let's talk about that. If we wanted to do this using a quantum computer, so starting with a collection of images, so starting with our classical data here, and we want to use a quantum computer to do part of this process, one possible path would be to take our classical data to then encode it into a quantum representation of the data. So take our images, translate them into something that has a quantum representation. Then we can use quantum machine learning, and I'll talk about what that is, quantum machine learning on that quantum representation of our data. And then perhaps we also can use some classical machine learning just to interpret the result, to interpret that final prediction. So that's what we're going to look at today for quantum machine learning, a quantum image classifier. So I'm going to slightly change the problem. Here we're going to use a standard data set. Instead of cat pictures, we'll be thinking of handwritten digits, and specifically handwritten 1s and 9s. And we'll want to say whether or not we get a 1 or a 9 through our model. So present a piece of information, and we'll want to say, yes, this is a 1, or no, this is not a 1, this is a 9. So our data is going to be images of 1s and 9s. The model we'll use is a form of a quantum neural network. So we'll have some quantum applications sort of inside the structure. And the prediction will say, if the model says true, then we'll classify that as a 1. If it says false, we'll say then it was a 9. So let's go ahead and look at the pieces we need to kind of build this sort of structure. And one of the things that we'll use, that I currently use in my work, is a quantum circuit. So quantum circuit models are the type of models that you would see, for example, on an IBM machine, an IonQ machine, a Rigetti machine, where you have a selection of qubits, and you can assign operations to each individual qubit in the form of gates. So for example, here's a Z rotation where I want to rotate the qubit 90 degrees in the Z basis. And here is a combined ZZ rotation where I'm rotating 2 qubits 45 degrees in the Z basis. And then here, this is where some of the machine learning comes in. If you notice, these rotations don't have an angle associated with them. We're actually going to learn which angles we need to get good predictions out of our circuit. So this is where the machine learning part comes in. Sometimes we don't specify a full, or we specify an initial set of instructions with the mindset that eventually we're going to tweak those instructions so that it fits our data. And then here on the end, I've also included some measurement gates, just as an example. So let's go ahead and look at how we take an image. So here are 1s and our 9s, and translate it into quantum data. So I'm going to talk about that in a second. So this is a big part of the work that we do at Quantum Computing Inc. We typically always start with the idea that our customers are bringing classical data to us and asking us to use some form of a quantum process to get a better prediction, a better answer than they can classically, or at least prepare them for the world where we have very powerful quantum computers to get very interesting answers out of them. So one of the things we have to do right now is we have to fit this classical data to a quantum process. And that's not always clear how that should be done. For example, here I'm showing just 3 qubits, and each of these images has 28 times 28, so about 700 pieces of information in them. It's not terribly clear how to take that information and translate it into just 3 operational qubits. So some of what we do is called preprocessing, where we take the classical information and perhaps we switch it into a different representation. So we reduce the size of the data. For example, I can take these images and translate them into a binary image where I don't see any gray information, and the size of the image is reduced from 28 by 28 to 16 by 16. So reducing that size of the information, and then on the classical side, and then from there, I need to come up with an encoding, some sort of set of rules to take this classical information and translate it into quantum gates. So for an example, what I could do is I could look at, the structure here in this reduced image, and I could say, okay, well, if the pixel value is between, let's say, 1 and 0.75, then I'll add a Z rotation of 90 degrees. But if it's lower, if it's between 0 and 2.5, maybe I'll add an X rotation of 45 degrees. And if it's not in between those 2 ranges, maybe I just don't do anything to the qubit. In this case, I kind of skip an operation. So that's a simple example of a type of encoding that we could do. Once we have the translation from image to quantum data, then what we can do is we can take our encoded data and add that circuit, what's called a variational layer or variational layers, that has the type of gates where we can actually tune the parameters, where the gates where we're going to change them as data is presented. And so we get to choose the type of gates that we use here. We also get to choose the structure of the gates, and there's lots of literature about how to do that for different applications. And then we'll add on some quantum measurement. So there we've prepared our quantum circuit. After the quantum circuit is prepared, then we can run it through a quantum machine or a quantum simulator, and we'll get measurement results. So let's say we did it 1,000 times, and this is the states that we get out of it. So we have a lot of information in the 0 state. Sometimes it gets mapped to the 2 state, sometimes the 16 state, and so on. We take this quantum result and we can feed it through a classical neural network, which will then give us that yes/no prediction that we wanted in the first place. And let's say we do that, and then we do it for these 2 images, and then this is the result that we get back. And we have to, in the end, we've gone through a lot of things, and we have to go back and we have to say, well, did we do a good job, really? And if we remember, very back at the beginning, I said, okay, we're gonna say true if the image is a 1, and then false if the image is a 9. And it doesn't look like we're doing a very good job just yet, but we didn't talk about how we train it. So we also have to take into consideration how we're going to train these different pieces, because the training procedure actually changes slightly because we have this combination of quantum and also classical architectures going on. The basic steps are fairly similar. We take our data, we translate it into quantum data, and then we present it, we add on the variational layer and so on. So we'll present data to the model, we'll calculate our prediction through the entire pipeline, then we'll look and see, oh, this 9 is not correct. We'll take that error and we'll send it through the classical model, and then we'll get the result backwards from the classical model. We'll tweak the variational layers in the quantum model, and then we'll run the circuit again. And that'll give us a different prediction. And hopefully this next time, after we've tuned these weights and tuned the weights here, hopefully the next time we get a better prediction, and we keep on doing that throughout the data. So going back to kind of this data science approach, what do we have to do for this quantum model? First off, we have to take our classical data, translate it into some quantum circuit-based information. That's our encoding piece. Then we have to add on our variational layers. We have to build our quantum model. We make a prediction, and then we have to make sure that we're getting good predictions by using a training process. And that's very similar, or it has the very same flavor of classical machine learning. It's just the way that we operate on the data changes slightly. We have to add an encoding piece. We have to, pay attention to how we are actually running our quantum circuits, whether that's in a simulator, whether it's on a quantum machine. Sometimes that gets a little bit expensive, so we want to be very mindful of that. But this is the type of thing that we do at Quantum Computing Inc. is we think about taking classical information and then moving it through a quantum process for customers. So I just wanted to take, before I open it up to questions, here I put down some different technical careers that we have here at Quantum Computing Inc. We hire people from a physics background, we hire research scientists, we hire software engineers, application engineers, and also data scientists. Those are just the technical careers that we have at our company. And we also hire people from a variety of backgrounds, whether that's computer science, physics, mathematics, business, all sorts of different backgrounds. So I just wanted to leave you with the impression that, coming from quantum, it's not all, or coming to quantum, it doesn't always take a well-defined path. For example, I don't have quantum physics in my background. I'm a mathematician by trade, working in the quantum computing space. And then of course I put down also some contact information. So we have a little bit of time. If anybody has any questions, I'd be happy to answer those. Maybe no questions.
I mean, very comprehensive.
Oh, thank you. Yeah, so feel free to reach out if you guys have questions, or if you want a copy of the slides. Maybe I'll send the copy of the slides out, or so you guys can put it. I think you guys have a Discord channel, right, for the hackathon?
Yeah, we do. If you want to, you can send me the link in the chat, like private message, and then I can put it in the Discord.
Okay, cool. Cool. All right, well, I hope